Hello. There seems to be a lack of easy to understand information out there about how feedback oscillators work, and to me it's a very interesting subject. Also, another thing is there's an important equation known as the Leeson Equation, which explains how the phase noise performance of an oscillator can be predicted, and this seems to be misunderstood and is often misrepresented, and so I thought I would try and clarify this. By a feedback oscillator, we're just talking about a normal oscillator that uses a positive feedback loop to produce an approximate sine wave output. And also a negative resistance type oscillator falls into the same category, and the same equations relate to it because a negative resistance is really a type of amplifier. We're not talking about relaxation oscillators, that's something a bit different. Now, the noise performance of an oscillator can be characterised as AM noise and PM noise. By AM noise, we're talking about sidebands around the carrier that cause amplitude fluctuation of the carrier, and by phase noise, we're talking about sidebands around the carrier that cause phase fluctuations from the ideal perfect constant frequency signal. We're not really talking about frequency drift here. That's more easily seen as a gradual change of frequency in the time domain. Here we're talking about things that cause fairly small fluctuations of angle of the ideal carrier. Now, amplitude noise on an oscillator is not really so important because it's only produced at fairly low levels in a normal oscillator, and it's easily removed after the oscillator if necessary, and it doesn't produce very serious effects in systems, whereas phase noise is produced at significant levels in an oscillator. It's not easily removed afterwards, and it has serious effects in modern systems.
I have heard quite a few incorrect negative things about the Leeson equation. In my experience, it does work and is very useful, and I think the negative things you hear about it result from a misunderstanding. You may think that you can do it all with CAD, but a computer won't think for you. It'll only crunch numbers or do what it's programmed to do. To think about something, you need to understand how it works. Understanding the derivation of the Leeson equation also gives a valuable insight into how an oscillator works. And oscillators might look simple things, but often the performance of a system is limited by the performance of the oscillator, and obtaining the optimum performance from an oscillator is not always a simple thing to do. The Leeson equation does relate to all feedback oscillators, but there are additional noise sources in some oscillators, especially quartz resonators and reactors and these sort of things. With ordinary LC oscillators, strip line oscillators, cavity oscillators, these sort of things, then in the minus 20 dB per decade region, the Leeson equation should give some idea what's going to happen. In engineering, phase noise is usually expressed as the power spectral density in one sideband to the carrier power ratio, so that's measured in dBc per hertz. So let's go and look at the Leeson 1966 paper. There have been papers after this, of course, on oscillators, but this paper and then the derivation of the Leeson equation, which came afterwards, really explains pretty much how oscillators work. So noise goes in various regions as you move out from the carrier, the offset from the carrier, and the noise mechanisms change a bit through those regions, and particularly the slope at which the noise goes down as you move from carrier changes. But Leeson's paper is most important for the minus 20 dB per decade slope, because in this region it's been shown that the equation is actually a linear model of what goes on inside the oscillator. So Leeson's equation gives the phase noise in terms of several parameters of the oscillator. So the parameters are the loaded Q, the carrier frequency, and then a power ratio, here, and if we look at this power ratio at the input to the sustaining amplifier, it is the density of the noise to the power at the input to the amplifier ratio. So here on the top we have the noise figure of the device, Boltzmann constant and temperature, and then on the bottom PS, and it says here PS is the signal level at the oscillator active element input. Well, Leeson's equation is often presented in various different ways, but an important thing to understand is that in Leeson's original paper, this ratio here on the bottom, PS, is the signal at the amplifier input, and often the equation is misrepresented, and this PS is called something else, the output power of the oscillator. You see this in all sorts of places, in textbooks, and this can cause a lot of confusion, of course, if you're not familiar with this field. People who work in this field and use this equation, of course, know how it works. But there is a good explanation as to how this misunderstanding came about. Leeson didn't actually derive this equation in his paper, he just presented it. And later on, Robbins published a derivation showing that this equation is actually a linear simulation of what goes on in the oscillator. And so this is Robbins' derivation, and so this is really the same as Leeson's equation we use nowadays, except that where Leeson had PS, here we have this C, which is said to be oscillator output power. Now how this change came about, we can see, because the oscillator circuit that Robbins simulated was not a completely general circuit. This is it here. This is the sustaining amplifier. It's a transconductance amplifier, so it's infinite input and output impedances. This resistance here represents the input impedance to the amplifier, a practical amplifier. This resistor here represents the load where the output power of the oscillator goes, and also the losses in this resonant circuit here. Now you can see if this transformer ratio is set up to provide best power transfer, which is what's described in the text, then the power in this resistor is equal to the power in this resistor. So the power in this resistor isn't exactly equal to the output power of the oscillator. There are losses in the resonant circuit, so the output power will be slightly lower than the power in this resistor, which in most cases makes this misunderstanding even worse. But you can see that neglecting the losses in this resonator, that with this circuit the input power to the sustaining amplifier is equal to the output power of the oscillator. Well, really for the general case we want an equation which doesn't have this constraint on it. In the next video we will go and look at how we're going to simulate a feedback oscillator in order to derive Leeson's equation, and in the video after that we will go and actually derive Leeson's equation. So this will be for a more general case, and we will show that what Leeson said is correct for the general case. Thank you for watching.